This is a pretty abstract problem, so we're going to take some time with our preparation. Okay, so here's the situation. We're using a microscope objective to make an image of a very tiny object. So we have a very tiny object here, and the object is about at the focal point, okay? The lens has a diameter d, okay? Now, in the book, we define something called the numerical aperture of the lens. Okay, and if we define this angle right here as phi 0, okay, so this side of this triangle is half the diameter of the lens, this side of the triangle is f, this angle here is phi 0. The numerical aperture of the lens is defined as n times the sine of phi 0. But n is the medium in which the object being imaged is placed. So that's if you have an oil immersion microscope, you'd use the index of oil. But in this case, we're told that it's in air. Okay, so the index of refraction is just 1. So the numerical aperture is just the sine of phi 0. Now let's take a look at this picture right here. If I make a triangle right here, this side of the triangle, the side adjacent to this angle, is a length f. This side of the triangle, which is opposite the angle, has a length d over 2. So I can say this. I can say the tangent of phi 0 is equal to the opposite side of the triangle, d over 2, over the adjacent side of the triangle, f. Okay? So here's my angle relationships in terms of the diameter of the lens and the focal length. And this angle is used to define the numerical aperture. But the problem asks about the resolving power. We have to resolve two objects 400 nanometers apart, and the book tells us this, okay? The resolving power of a microscope, which is defined as the minimum distance between two objects that can be resolved, is equal to 0.61 times the wavelength of light being used, and it's theta 0 because it's the wavelength in vacuum. But the wavelength in vacuum is the same as the wavelength in air, and that's 550 nanometers, so we can just use that, divided by the numerical aperture. So we're asked this. We want to resolve objects that are 400 nanometers apart with a lens of 1.6 millimeter focal length. We need to know what diameter the lens has to have. Whew. So let's take a look at where we're at. We know d min, okay? We know the size of the object that has to be resolved, okay? We know this is 400 nanometers. We know the wavelength of light, that's 550 nanometers, okay? So we can figure out the necessary numerical aperture. If we know the numerical aperture, we can figure out what phi 0 is. And if we know what phi 0 is, and we know what f is, we can figure out what diameter of the lens is necessary. So there's a fair amount of manipulation, but it's all reasonably straightforward after we've done this preparation. Now let's go ahead and complete our solution. And it's going to work like this. We'll take this relationship right here. Okay, the minimum distance, okay, d min is equal to 0.61 times lambda 0 divided by the numerical aperture. We want to solve for the numerical aperture. Well, the numerical aperture is just equal to 0.61 times lambda 0 over d min. Lambda 0, that's just the wavelength of light, and it's the wavelength in vacuum, but that's the same as the wavelength in air. So this is 550 nanometers. D min is the features that we're trying to resolve, which is 400 nanometers. By the way, I'll point something out here by way of kind of like assessment as we go. We're told that microscopes can resolve objects down to about 1/2 of the wavelength of light. So 1/2 of 550, 275, these are farther apart than that, and so it is theoretically possible to do this, but it's going to be at the edge of what's possible, okay? Now, since it's nanometers over nanometers, I can just keep them in nanometers, and the units will cancel, and I can solve for the numerical aperture. If I do that, I get a numerical aperture of 0.839, and I'm going to keep an extra significant figure. This is a two significant figure problem, but at intermediate stages, I'll keep extra sig figs. Now remember, we said the numerical aperture was just equal to the sine of phi 0. And so I can calculate this. Phi 0, that angle is just 57.0 degrees, this angle right here. Now notice something else by way of assessment, okay? We said here, by way of assessment, that this is theoretically possible, okay? So that's good. Also, we said it was going to be at the edge. In the book, it says that the maximum numerical aperture for resolution for imaging in air is about 0.95. We said we'd be close to the maximum, and in fact we are. So our assessment is this is close to the edge. Still possible, but close to the edge of what's possible. Now we have theta 0, or phi 0, and so we can use this relationship right here. I'm looking for d. I'm going to take this relationship and rewrite it this way. D is equal to 2 times f times the tangent of phi 0. Well, I know what phi 0 is. Phi 0 is 57 degrees. Okay, so that number goes here. I also know what the focal length is. The focal length is 1.6 millimeters. And I'm just going to keep this in millimeters. I'm going to multiply it by the tangent of phi 0, which is just a number. And so I'm going to get an answer in millimeters. And if I do this, for d, the diameter of the lens, what I get is this. I get a diameter of 4.9 millimeters. Now take that back to our picture. If this is 4.9, this is 1.6. That's a pretty big angle, but we came up with 57 degrees. That's at near the limit of what's possible. And so our results makes sense in terms of our picture and in terms of our understanding about what numerical aperture means. And so everything looks good. This matches with our expectations of the way the world works.